In this exercise, we're going to take a look at PI control tuning. Tuning a controller is very similar to tuning an instrument in that we have rough correlations which give us an idea of where we should start, but the tuning depends on what our process is. If we have a process for a biological reactor where we don't want to overshoot or kill our specimen, it's much more important to not overshoot than it is to reach that set point fast. Other applications may require a very fast time to reach the set point. And so after we have our controller, the next step is to tune it, looking at our application and looking at how our controller performs in that application. So we're going to look at IMC aggressive tuning and ITAE tuning. We've talked about those briefly before. I have our process constants written down. We'll go ahead and we'll look at what the gain and the integral gain are going to be for each of these constants. We'll go ahead and I'll just type them out real quick. Great, so I just went ahead and I plugged in these constants, the IMC tuning constant right here, and the tau and the ITAE tuning. So we can look at what both of those values are if we briefly run this section. Now if we have these, let's go ahead and let's go to our PI control simulator. And let's change our kc and our tau y to match each of these and see which one performs better. Let's first try with the IMC tuning. So a kc of about 5.9. So about 6. And a tau y of 175. So the integral of absolute error is 1150 roughly. Let's now look at our ITAE. Oof, hard to say today. And it's roughly similar. We'll go ahead and I'll change these controllers really quick. So this step is in terms of 1. And on this controller, so the step is in terms of 0.1. Now it can be a little bit more specific. So the other one has about 6.2 and 172. So we're a little bit better. 1094. For our integral of absolute error. So let's go ahead and let's implement the ITAE tuning then. So we're now going to validate this actually using MATLAB or Simulink. We'll go ahead with MATLAB first. Within MATLAB, we're going to look at with the solution. Here we have the ITAE solution, KP of 0.9. Let's make sure so KC we want at 6.18 and 172.26. Actually, since we want ITAE, that's what the variables are going to remain. So we'll just go ahead. Actually, they're right there. Perfect. On the right. We're going to go ahead and we make the arrays like our loop, like normal. Then we'll go ahead and loop through. And then we'll record the measurements. We'll create a figure. We'll record the time, and we'll look at a plot as we go over time. Again, we're using our PID controller as we have other times. The PID controller will take arguments of the parameters, the set point, and other variables. The point here we want to make is just looking at how we tune. If we look at as we change K, the gain, you can see that we have an increase in oscillation. As we increase or decrease I, you can see that the integral control changes and we're a little bit less aggressive as far as that persistent offset. There's also a little bit less oscillation. So we're just looking at how can we best configure our controller. You'll notice as we tune these down, we can get a little bit better error than some of these correlations. And then that may be mostly due to that oscillation that occurs. As we have tau I quite high, it's a little bit more sluggish in getting to to that final solution. Again, tau I being large is a conservative tau I. The smaller tau I is, the more aggressive it is to penalize persistent offset. So let's go ahead and let's run a MATLAB script and look at what happens. Go ahead, we'll run this section now, and we'll watch our graph. All right, we've just completed our first round. I also want to point out a couple of things. This is our simulated one. Here's our actual one. Number one, you'll notice we started a little bit high. I accidentally turned on the heater while we were discussing earlier, so the heater was already a little bit warm. You'll notice that I printed out the integral of absolute error, then it was equal to 21.6. In my code, I had the outputs being IERR right here, which caused the output to be integral. That was actually, how can I say? I was printing the proportional term for the output rather than the integral of error. And so I don't have our full integral of error here in this code, but I can calculate it real quick, and I'll just do it with the command window. The way we'd get the integral of error is if we just assume every one is about 1 second apart. We can do this just by taking the sum of the difference between setpoint 1 minus, so we'll do sum of setpoint 1 minus t1. You'll get an integral absolute error of about 2,500, which is obviously more. If we look at how the graph looked, though, it wasn't having that oscillation we see here and that persistent offset after it reached close, but not quite. You can notice, though, that toward the end, our heater was starting to ramp up more and more, trying to counteract that persistent offset that was occurring. I'll let you go ahead and do the ITAE, the IMC tuning and see which one performs better for yourself. And we'll go ahead and look at also how to tune in Simulink.